All right, now that we have a right understanding of the following factorial in terms of ordinary factorials, let us turn to the binomial. Now, let us begin with a ratio. Look at the ratio of n factorial to k factorial over n minus k factorial. Let's begin by grouping terms, pulling out the term k factorial in the denominator and expanding out to see what we get. Now, the moment we pull out k factorial from the denominator, what remains, we recognize, is exactly our old friend, n to the k falling. And therefore, that expression in the middle is exactly n to the k falling over k factorial. But we pause, we reflect, and we say, we have seen this before. In fact, this is exactly the binomial coefficient n choose k. And so we've discovered a new representation for n choose k. N choose k may also be written in an equivalent formulation as the ratio of n factorial to the product of k factorial and n minus k factorial. But we shouldn't rest on our laurels. The form in the middle suggests another decomposition. What if we pull out the term n minus k factorial? And now let's see what happens as our expansion moves to your right. If you pull out the term n minus k factorial in the denominator, what remains is n factorial over k factorial. And we recognize from the previous slide that this is just another name for n to the n minus k falling. And so this expression becomes n to the n minus k falling divided by n minus k factorial. And we recognize in here another binomial coefficient. It is exactly n choose n minus k. And we've discovered a beautiful binomial identity. N choose k may be written in terms of falling factorials. It may be written in terms of ratios of factorials. It may be written in terms of quite another binomial coefficient. Now, this kind of identity and this ability to move freely between different representations turns out to be, from an analytical point of view, extraordinarily useful. Now, we've derived these formulae by just algebraic manipulation. Where does this actually lead to? Can we think of this in a more visual way? Is such an identity transparent? Is it obvious? Does it fall into our laps if we just look at the problem holistically? Indeed it does. In combinatorial settings, it is frequently the case that algebraic computations may be replaced by purely combinatorial logical arguments. Let us illustrate this in this setting. So let's start with our binomial identity, n choose k equal to n choose n minus k. Now recall that the binomial coefficient arose in characterizing the number of different subpopulations we can engender by sampling from a larger population. So imagine that we've got a population of size n. We select k from this population. This is what you will see on your left-hand side. You've selected k out of this population of size n. There are n choose k ways of doing this. Now, the moment you specify k, that means you've left out n minus k members of the population. Specifying those that are selected is equivalent to specifying those that are not selected. And therefore it becomes obvious that, in fact, n choose k must be exactly n choose n minus k. Here's a purely combinatorial argument for this kind of identity.